And let's try to figure out whether we can minimize or maximize this. Well, so what we'd start doing immediately is taking the partial derivatives. Okay, so what is f sub x? It starts with 2x minus 2y plus 0 plus 2. Okay. Remember that y is a constant, so this differentiates to 0. Now if we do f sub y, that's going to be, well, 0 minus 2x plus 6y minus 2. And what we want to do is set these things equal to 0. And we want to solve these two equations at the same time. Okay, so an important thing to remember, I mean, maybe I should have told you a couple of weeks ago already. If you have two equations to solve, well, it's very good to try to simplify them by adding them together or whatever. But you must keep two equations, okay? If you have two equations, you shouldn't end up with just one equation out of nowhere. Okay, so for example here, we can certainly simplify things by summing them together. See, if we add them together, well, the x's cancel and the constants cancel. And in fact, we're just left with 4y equals 0. That's pretty good. That tells us y should be 0. But then we should, of course, go back to these and see what else we know. Well, now it tells us, so if you put y equals 0, it tells you 2x plus 2 equals 0. And that tells you x equals minus 1. Okay, so we have one critical point. That's xy equals minus 1 and 0. Okay? Any questions so far? No? Well, you should have a question. The question should be, how do we know if it's a maximum or a minimum? Well, yeah, so if we had a function of one variable, we would decide things based on the second derivative. And in fact, we'll see tomorrow how to do things based on the second derivative. But that's kind of tricky because there's a lot of second derivatives. I mean, we already have two first derivatives. You can imagine that if you keep taking partials, you may end up with, more and more. So we'll have to figure out carefully what the condition should be. So we'll do that tomorrow. For now, let's just try to look a bit at, how do we understand these things by hand. So, in fact, let me point out to you immediately that there's more than maxima and minima. So remember, we saw, the example of x squared plus y squared that has a critical point. That critical point is obviously a minimum. And of course, it could be a local minimum because it could be that, if you have a more complicated function, there's indeed a minimum here, but then elsewhere, the function drops to a lower value. So we call that just a local minimum to say that it's a minimum if you stick to values that are close enough to that point. Of course, you also have a local maximum. Well, I didn't plot it, but it's easy to plot. Okay? That's a local maximum. But there's a third example of critical point, and that's a saddle point. Okay, so the saddle point, it's a new phenomenon that you don't really see in the single variable calculus. It's a critical point that's neither a minimum nor a maximum, because depending on which direction you look in, it's either one or the other. So here, see the point in the middle at the origin is a saddle point. If you look at the tangent plane to this graph, you'll see that it's actually horizontal at the origin. You have this mountain pass, at a mountain pass, the ground is horizontal. But depending on in which direction you go up or down. So we say that a point is a saddle point if it's neither a minimum nor a maximum. Okay, so possibilities could be a local mean, a local max, or a saddle. Okay, so tomorrow we'll see how to decide which one it is in general using second derivatives. For this time, let's just try to do it by hand. So I just want to observe. In fact, I can try to, these examples that I have here, they're x squared plus y squared minus x squared. They're sums or differences of squares. And if we know that we can put things as a sum of squares, for example, will be done. So let's try to express this maybe as the square of something. Well, so the main problem is this 2xy. But observe, we know something that starts with x squared minus 2xy that is actually the square of something else. Right? It would be x squared minus 2xy, well, plus y squared, not plus 3y squared. So let's try to do that. So we're going to complete the square. So I'm going to say it's x minus y squared, and then, so that gives me the first two terms and also a y squared. Well, I still need to add two more y squares, and I also need to add, of course, the 2x and minus 2y. It's simpler, it's still not simple enough for my taste. I can actually do better. See, I mean, now so these guys look like a sum of squares, but here I have this extra stuff. But 2x minus 2y, well, that's twice x minus y. It looks like maybe we can modify this and make this into another square. Okay, so in fact, I can simplify this further to x minus y plus 1 squared. See, that would start like, maybe I should put parentheses here. That would be x minus y squared plus twice x minus y, and then there's a plus 1. Well, we don't have that plus 1, so let's remove it by subtracting 1. Okay. Oh, so let me write that minus 1 here, and I still have my 2y squared. Okay, do you see why this is the same function as that one? Yeah? So, again, if I expand x minus y plus 1 squared, I get x minus y squared plus twice x minus y, that's those guys, plus 1. But I will have a minus 1 that will cancel out. And then I have a plus 2y squared.